All right, let's dive into one of the trickiest problems out there in modern software. How in the world do you get anything done when your system is spread out across, I don't know, dozens of services, and you know any single one of them could just fail at any second?
But before we get into the nuts and bolts, let's just start with a kind of radical idea. What if we stopped trying to prevent failure? What if, instead, we just accepted that things are going to break and we built our systems to handle it gracefully right from the get-go? To really get why this is so important, we have to look at how much the world has changed. Back in the old days of monolithic apps, you had one giant database. You could just wrap a whole bunch of operations in a single all-or-nothing transaction. It was simple. But in this new world of microservices, oh man, a single click from a user, like placing an order, might need to write to 5 different services, and they each have their own database. That old model, it just completely shatters. And that leads us right to what our source material calls the transaction myth. It's this belief that we can somehow still apply those old, rigid, all-or-nothing rules to our new, flexible, and honestly, sometimes chaotic systems. It just doesn't work. So the guide from Wix's engineering team lays down this really stark, powerful rule. They do not use transactions across services, ever. And this isn't a limitation, you see. It's a core design principle. It forces you to assume that any write after that very first one could fail, and you have to build your entire system around that reality. Okay, so if you're gonna just throw out all the old rules, what do you replace them with? Well, it turns out you need a whole new philosophy for building software. And here's a great summary of that philosophy. From now on, your transaction is just one single database write. That's your boundary. Everything else, all those side effects, they get kicked off asynchronously through a super reliable message bus, like Kafka. And all of this leads to the most important point on this slide. You have to design for partial failure. You have to plan for a world where step 1 works, but step 2 just doesn't. Okay, so that's the big idea. But how do you actually build this stuff? Let's take a look at the essential toolkit, the building blocks for making this all work in the real world. First up, domain events. The easiest way to think about this is like a public announcement system for your data. When an order gets created, the order service doesn't have to go and call the shipping service and then call the email service. Nope. It just yells out into the void, "Hey everyone, an order was created," and broadcasts that to Kafka. Any other service that actually cares can just listen in and react on its own time. Next is something called the async task queue, or ATQ, and this is a really brilliant pattern. It's kind of like sending a reliable, retriable message to your future self. A service can give itself a task to do later by sending a message through Kafka that loops right back to itself. This makes sure the task is durable, it'll survive a server restart, and it gets retried automatically if something goes wrong. So here's the whole toolkit in one place. You've got domain events to announce changes to the world, the ATQ to schedule work for yourself, Kafka's built-in retries as your automatic safety net, and this thing called an execution guard. It's what makes sure a task doesn't accidentally run twice. We're going to talk a little more about that one in a bit. So how do we actually put this toolkit to use? Well, the source guide gives us a really practical playbook with 3 powerful patterns for handling pretty much any kind of write you can think of. Pattern number 1 is the zombie pattern. And I gotta say, I love this name. The idea is, first you create your record. Let's say it's an order, but you put it in a pending state. This is your zombie. It's in the database, but it's totally invisible and harmless. Then you go and try the risky thing, like charging a credit card. If it works, great. You just update the order state to active. If it fails, no problem at all. The harmless zombie just sits there, not causing any trouble for anyone. The second pattern is the async follow-up. And this is your workhorse. This is the one you'll use all the time. The user gets an immediate success message because you do that one critical write right away, synchronously. Then all the follow-up stuff, sending emails, updating analytics, you name it, gets triggered in the background. The user gets a super fast, snappy experience, and the system just reliably handles the rest. And finally, for those really long-running, complex jobs, there's the full async pattern. With this one, the server basically responds immediately with, "Yep, got your request, here's a job ID." All the heavy lifting then happens in the background. This is great because it avoids those frustrating timeouts and gives the user a clear way to check on the progress of their request. But here's what's so great about this guide. It's pragmatic. It knows that doing things the ideal way takes real effort. And sometimes, you know what? A shortcut is fine. If a second write almost never fails and the risk of an orphaned record is low, maybe just do 2 synchronous writes. The key here is to make that trade-off consciously and only choose the simpler path for your low-stakes flows. Now, once you jump into this async world, you have to learn to master its unique challenges. Specifically, you've got to tame the chaos of what they call at least once delivery. So Kafka guarantees that your message will be processed at least once, which means, yeah, it might be processed more than once. Now, this could be a total disaster if that action is something like charge the customer's credit card. The solution is a concept called idempotency, making sure an operation can run multiple times and have the exact same result as running it just once. And you can do this with that execution guard we mentioned, which basically acts like a bouncer, making sure a potentially harmful task only gets to run one time. The other classic problem is a task that just runs for way too long. Kafka might think the process died and then reassign the task to something else, which can lead to duplicates or even infinite loops. The solution is actually pretty simple. Don't do one massive job. Instead, break it into hundreds of tiny, fast little chunks. That way, if any one chunk fails, the job can safely pick up right where it left off. So when you pull all of this together, it's way more than just a set of tools. It's a complete shift in your mindset. It's all about embracing this new reality and learning how to spot the traps from the old way of thinking. And the biggest trap of all is what the guide calls async revert. This is that gut instinct to try and undo step 1 if step 2 fails. But what if your undo operation also fails? Now you're in an even worse mess. The right way is async retry. Don't try to go backward. Just keep trying to move forward. Just try step 2 again. It's so much simpler and way more reliable. And this quote just nails it. This is the ultimate takeaway. This is the core principle of everything. You design your system for a safe partial state, like our harmless little zombie entity, and you use asynchronous retry as your recovery plan. That is the foundation of a truly resilient system. So I'll leave you with one final question to think about. Take a look at the systems you build, the ones you work on every day. Where are they most fragile? And could embracing this philosophy of designing for failure instead of against it be the key to making them truly unbreakable?